Hey everybody! This is the last open-ended question in exam 3. This one has to do with redox reactions and voltaic cells. So let's get started. Maybe we can do this. Now this is a question where you have to answer all these parts for both A and B. Okay. So the first one is balance reaction using the half reaction method. Okay, now these should be super simple to balance using the half reaction method. So it's Al3 plus goes to Al. And so we're going to add 3 electrons here. And then it's Li goes to Li1 plus. And so we're going to add 1 electron here. So when we balance this thing, we want to multiply this by 3 to get that out. And so now the coefficients here, and I'll just write them here, is 3 and 3. Okay, so that's the balanced chemical reaction. Okay, so now we want to calculate the standard cell potential. To calculate the standard cell potential, we need to know the value of the cell of the half reactions. We need to know the value of the standard reduction potential for the half reactions, and then we also need to know which one's the reduction and which one's the oxidation. So remember, reduction is gaining electrons, so Leo-Ger. So this is the reduction reaction, and this is the oxidation reaction. Okay, and conveniently, I gave you this sheet of cell potentials to find out which one, so that you can look up the ones that you want. And so we have aluminum and lithium. Okay, I feel like aluminum and lithium. There's lithium, or there's aluminum. I'm having a hard time talking today. And there's lithium. Okay, and notice when we solve this, it's the cell potential equals the reduction potential at the cathode minus the reduction potential at the anode. And so remember, it's a red cat, an ox. So the cathode is aluminum, so that was negative 1.66 minus a negative 3.05. And so when we did that, we get that the cell potential equals 1.39 volts. Okay. I need the calculator to do that guy. Okay. Now, let's do the finding the. We want to find the free energy. So delta G equals negative NF, and it's a fancy F, but sometimes they write it like that, and then E naught cell. So delta G we don't know, so this is for part C. Okay, this is B, this is A. Okay, so for part C now, N is the number of electrons that have been transferred. F is Faraday's constant, which is given to you right up here. And the cell potential we found out in part B. Okay, so we figured this out, and this is in joules. So I just did the math and plugged it in the calculator, and that is equal to negative 402 kilojoules. Now for part D, whoops, we want to find the equilibrium constant. And so the equilibrium constant, the formula is right here. So that's ln K equals N cell potential E divided by 0.0257. Now, let me bring up my calculator and we'll actually do this one. So how many electrons are being transferred? Again, it's 3 electrons being transferred. So that's 3 times the cell potential. So it's, and now we take that and we do e to that answer, and we get some sort of crazy number like K equals 2 times 10 to the 70. Okay, all of that to say is this reaction is very, very, very products favored. Okay, now the last thing is taking this and drawing a voltaic cell with it. Okay, so we go here. I'm going to erase all of this because I need space. I'm going to leave the reaction. So I left the reaction here, and so all I'm going to do is I'm going to draw a generic voltaic cell. Those are the electrodes, pieces of metal. Okay. And then here's our salt bridge. Okay. Once we have that, now we can start labeling. One of these things is going to be aluminum, so that's that one. I just randomly picked it. Then there's Al3+, that's that. Okay. The metal and the ion go together, and now we go Li and then Li+. Okay, and then the metal and the ion go together. And remember, aluminum was the cathode. So this is the cathode, and this is the anode. And now which way do the electrons flow? The electrons flow out of the anode. They're given up by the anode. Okay, and into the cathode. And now the ions will flow this way to keep the circuit going. And now the charge on the cathode and the anode. Remember, cats are positive, so that's positive in the anode, and against or negative. Okay, so that's the first part of that question. So now we're going to do the second part of this question, and it's practically the same thing, okay, and we'll do it maybe a lot quicker. Okay, so I'm going to break this into half reactions and balance it. So that was balanced. That's awesome. Okay, and now we're going to calculate the cell potential. So again, E naught cell. So we need to now figure out what the cathode and the anode are, and we do that by determining what's being reduced and what's being oxidized. Okay, so this guy is being reduced, this guy is being oxidized. Okay, so now this is the reduction, this is the oxidation. So this is the cathode, this is the anode. Okay, so now all we have to do is look up the values for silver and iron. Potential of the voltaic cell. Okay, so now we do the same thing that we did before with delta G, using this formula. Delta G equals negative NF E, and so we have F. N is the number of electrons being transferred, which in this case is 2. and then E we just calculated, so let's do that. At negative 239 kilojoules, great. And we know that that's cool because this, a positive cell potential, means it's spontaneous, and a negative delta G means it's spontaneous. Okay, and now we do the same thing with the K. Okay, so we have the formula. Plug in and chug. So that is our equilibrium constant. Now we're going to draw the same picture, voltaic cell. So that goes through the whole thing there. So that was pretty crazy, but there it is, the third question for exam 3. Have a great day.